Well, welcome to the last unit in this short course. In the first 4 units, we developed a very sound physical understanding of how MOSFETs operate, all the way from the micron scale dimensions when MOSFETs were first developed in the 1960s and 1970s to the nanoscale dimensions of current day technology. In Unit 5, there are a number of additional topics that you should know something about. We're going to begin by talking about the limits of MOSFETs. How small can we make MOSFETs? Now, I'll specifically be considering the limits for digital logic, and we'll be asking 3 questions. What are the fundamental limits of MOSFETs? How small can we make them? Questions like that. How close to the limits is present-day technology? And what, in practice, sets the practical limits of MOSFETs? We're going to use our energy band model for the MOSFET to address these questions. This gives us a very simple, very physical way to understand the operation of MOSFETs. In the off state, there is an energy barrier, E source to top of the barrier, that prevents the current from flowing, even though we've applied a large voltage between the drain and the source. There's an even bigger energy barrier between the drain and the top of the barrier. Now, in the on state, we push the energy down with a high gate voltage. Electrons then are free to flow across the device into the drain. Once they flow into the drain, they dissipate their energy and relax down to the bottom of the conduction band. This is going to be our simple physical picture, and we will address some of the limits with using some very simple physical arguments. Now, the arguments that I'm going to be using are similar but not identical to the arguments in this paper. You may want to have a look at that paper to get a slightly different perspective on the same limits, but we'll end up with the same answers. Here are the 3 questions. What is the minimum energy that it takes to convert a 1 to a 0, or vice versa? What is the minimum channel length that a MOSFET could ever have and still operate as a MOSFET? And what is the minimum switching time? How fast could we convert a 1 to a 0 and vice versa? So let's begin with question 1, the minimum switching energy. We have an energy band diagram where we have applied a large gate voltage, pushed the energy barrier down. Electrons with thermal energy in the source flow across the barrier now. There is no barrier. They flow across the channel into the drain, and then they dissipate that energy through various inelastic scattering processes, and that energy is dissipated. That's the energy that it takes. There's no current flowing in the gate, so in principle it doesn't take any energy to push the barrier down in the gate. It only takes this energy that we dissipate in the drain. Okay. Well, if we have a switching event, we have to ensure that when electrons get in the drain, they can't be thermionically emitted and go back over the barrier into the source, or else a switching event has not occurred. So we have to require, from a fundamental perspective, that the probability that an electron can be thermionically emitted over that barrier and go back to the source has to be less than a half, so that a switching event did occur. An electron did move from the source to the drain. So we know that the probability of being thermionically emitted over that barrier is e to the minus barrier height over kT. That probability has to be less than 1/2. The minimum then is when the probability is 1/2, we can determine what that barrier height has to be. And remember, that barrier height was the amount of energy that we had to dissipate or shed when the electron entered the drain. We simply solve this expression, and we get an answer. The minimum energy dissipation for a switching event is kT log 2. Now, this is a very familiar answer that is derived in many different ways. Oftentimes, it's derived from thermodynamic arguments. So this is a very fundamental lower limit. In practice, it's going to take much more, but this is the lowest it could ever be to have a real switching event that occurred. kT log 2. That's worth remembering. Now, let's think about the minimum channel length. This is the second limit that I'd like to address. Now, we can get a physical understanding by some detailed numerical simulations. Here are simulations of quantum transport in a nanoscale MOSFET. If we start over here with a fairly long channel, 13 nanometers, the red here indicates where the current is flowing. The current here is flowing over the top of the barrier. This is the way a MOSFET is supposed to operate. If I push the barrier down, more current will flow because the probability of hopping over that barrier increases. That's a classical MOSFET. If I make the channel length a little shorter, go down to 10 nanometers, you can begin to see a little bit of quantum mechanical tunneling underneath the barrier, but not very much. If we make the channel length even shorter, 7 nanometers, you can now see that there's a significant amount of tunneling underneath the barrier. And if we go all the way to 4 nanometers, well, we really probably gone too far there then, because the electrons just tunnel through that barrier even though the device is supposed to be off. The barrier has become transparent to the electrons because there's a high probability of quantum mechanical tunneling. So fundamentally, direct tunneling through this energy barrier is what is going to set the limit for how short we can make the channel length. Okay, so let's see if we can address that with our simple model and some simple arguments. We now have a large barrier because we're off. We have an electron in the source, and the probability that it tunnels through that barrier has to be less than a half in order to say that we're off. All right? That's a pretty loose definition of off, but we're only looking for some very general, very fundamental lower limits. Now, these tunneling calculations are things that we can do. You learn how to do them in a basic quantum mechanics course. It's a widely used approximation for doing these calculations is called the WKB approximation. And if you go through that, and you can find this in many textbooks, you'll see that the probability of tunneling through a barrier goes exponentially with the barrier height and with the thickness of the barrier, which is our channel length. If we say that that probability at most can be 1/2 to assure that we are off, then we simply solve that expression, and we will find that the channel length must be greater than h bar over square root of 2m times the height of the energy barrier, right? There is a constant on the order of unity that I'm throwing out when I do this argument, but we're only looking for some very general fundamental limits. Now, we will make that energy barrier as small as we can. We'll make it the minimum switching energy height so that everything is symmetrical. And then we arrive at a fundamental definition of the minimum channel length due to quantum mechanical tunneling. We have a simple expression here. It's related to the minimum switching energy. Third limit, what is the minimum switching time? So in this case, we've pushed the energy barrier down. The electron goes across the channel. It goes across the channel at a certain velocity. It had a thermal velocity in the source. It gets injected into the channel. It flows across the channel and comes out the other end. The time it takes then to go across the channel is the transit time of the channel, just the length of the channel divided by the velocity of the electrons. So the minimum transit time then is the minimum channel length divided by that injection velocity. In the non-degenerate case, that injection velocity is the unidirectional thermal velocity. The minimum energy is related to kT, so we can relate that kT to the minimum switching energy. We can throw away some constants that are on the order of 1, and we end up with a simple expression for the minimum switching time, h bar over the minimum switching energy. Okay, so the arguments are very simple. They're a little bit hand-waving, but we're only looking for some rough estimates of how small MOSFETs can be and still function as digital devices. Here are the results. We have the minimum switching energy is kT log 2. That's a very small number. We have the minimum channel length, and it depends somewhat on the material, on the effective mass of the semiconductor. If I assume that the effective mass is 1 times the electron rest mass, I plug in numbers and I'll find that the minimum channel length is about 1.5 nanometers. And the minimum switching speed, I just plug the numbers in, it's about 40 femtoseconds. So these very simple arguments give me these general fundamental limits for these 3 quantities of interest. Okay. Now, as I mentioned earlier, the minimum switching energy from our simple sort of hand-waving argument can be done in a much more fundamental way using thermodynamic arguments, but the same answer results. kT log 2 is the minimum switching energy. It's also worth noting that one can obtain these fundamental limits very fundamentally, the thermodynamic arguments for the minimum switching energy, but also with the two quantum mechanical uncertainty relations, we can get the minimum channel length and the minimum switching speed. So the fact that these can be done with very fundamental arguments, not specific to a MOSFET itself, suggests that these are fundamental limits for any kind of switching device that we might imagine. Okay, so that means that it is unlikely that we'll be able to invent a device that has fundamental limits that are better than a MOSFET. So the key question will be, how close to those fundamental limits can MOSFETs get? Is there another device maybe that could get closer to those limits? So let's address that question. How close are we with current day state-of-the-art technology? And I'll just use 22 nanometer technology as an example. Here are some approximate numbers for 22 nanometer technology for the power supply voltage, the inversion capacitance, the gate capacitance. Then I'll assume that the width and the length are as small as they can be, 22 nanometers. I'll assume an on current of 1 milliamp per micrometer, which is pretty typical of modern day devices. And we'll just take a look at some of the numbers. Our minimum switching energy for the MOSFET is going to be 1/2 gate capacitance times drain voltage squared. Simply plug in numbers. What we will find is that that's 1,200 times the minimum switch, the thermodynamically minimum switching energy. So it's a few orders of magnitude above. But remember that the minimum switching energy would basically assume a probability of 1/2 that the switching event occurred. We need much higher probabilities to have low error digital processing. We need about a factor of 10 to the 4th between on and off. So it's not surprising that in practice the minimum switching energy will be considerably higher. Minimum channel length, well, this is a 22 nanometer technology. Actually, that's within about an order of magnitude of this fundamental limit of about 1.5 nanometers. So we are relatively close to the minimum channel length. We can maybe get a little bit closer. And the minimum switching time, well, we would do the device delay metric. Gate capacitance times drain voltage is a charge in the device. On current is charge divided by unit time. That would basically give us the transit time of the device. That's about an order of magnitude above the fundamental limit. So we really are relatively close to the fundamental limits, and we may get a little bit closer, but we're getting relatively close with the MOSFET to some quite fundamental limits for these devices. Okay. Now, what sets the limit in practice? So in practice, the switching energy is set by two things, the switching capacitance and the power supply voltage. The power supply voltage, because of the IV characteristic of a MOSFET, because of the minimum subthreshold swing of 60 millivolts per decade, because of the need for low error computation, we have to have a large ratio between the on current and the off current. That requires us to have a power supply voltage that is much larger than the minimum power supply voltage that would fundamentally a device could still operate with. That minimum would be KT log 2 over Q. The minimum actually turns out to be closer to 1 volt, which is much larger for a practical device with a reasonable on-off ratio. There's also an awful lot of capacitance. We're wiring up lots of gates with lots of fan-out, with lots of interconnect wires, with parasitic capacitances. There's a lot of capacitance to charge too. So in practice, the minimum switching energy is orders of magnitude above the fundamental limit, and it seems quite difficult to get that much lower. Okay, in practice, the switching capacitance per node might be on the order of a femtofarad per node, not attofarads, which the device itself has from its gate, but all of the wiring and parasitic capacitances also. And as I mentioned, the power supply itself is far greater than the fundamental limit, lower limit power supply, because of the need for large on-off ratios. Okay, how about minimum channel length? That's set by quantum mechanical tunneling. You know, we really assumed an on-off ratio of about 1 when we did that calculation. We need a much larger on-off ratio, which means the channel length has to be longer. So that's one factor. The other very important factor is that what device designers really struggle with is electrostatics. We need not just to prevent quantum mechanical tunneling, but we need an electrostatically well-designed transistor that has a low subthreshold swing, that has low dibble, and in practice, that is what is determining the channel length so far these days, not quantum mechanical tunneling. That's what's led to the replacement of planar MOSFETs by FinFETs to try to control short channel effects and 2D electrostatics. Eventually, gate-all-around devices or nanowire devices may be the next step in trying to control electrostatics before quantum mechanical tunneling eventually produces a fundamental limit. Now, the increasing cost of the lithography needed to produce these very fine lines for the short channel lengths is also a factor that's becoming more and more important from a practical point of view. Speed limits. So if we look at the speed of a device, it's the device delay metric is the capacitance of the device times the power supply divided by the on current. The device capacitance includes not just the intrinsic gate capacitance, but a larger and larger fraction of parasitic capacitance as the device footprint is scaled down. Now the fringing fields from the gate electrode can fringe out and touch the metal drain electrode. There will be a capacitance between the gate and the drain, and it's very difficult to make that small. It's becoming a larger and larger fraction of the total capacitance. So that's one factor, a very important practical factor, the increasing importance of parasitics as we scale the device dimensions down. Okay, so that was a quick look at fundamental limits. How remarkably close to some of those limits we are with current day technology. Just to summarize the key points, you should recognize that modern day CMOS technology has been pushed surprisingly close to some very fundamental limits. There are practical technology considerations that continue to make it harder and harder to push further. We'll probably push a little bit closer to those fundamental limits, but parasitic resistance is becoming a very key issue, parasitic capacitance. There are other factors such as tunneling currents that are setting practical limits of the device. And the third point is that the fact that these fundamental limits can be described from some very general thermodynamic and quantum mechanical arguments. We obtain the same limits that we obtain for a MOSFET, suggests that it's unlikely that there is some magic device out there which will get us closer to these fundamental limits for switching devices. Okay, that's a quick look at some very fundamental limits for digital switching devices. As I said, Unit 5 has a number of topics that we should know something about. In this course so far, I focused on digital MOSFETs for digital logic applications. We've said a little bit about analog and RF, but there are other applications for transistors and there are other kinds of transistors. What we'll do in the next lecture is to show that there is another important application for MOSFETs besides digital logic and RF analog electronics, and that's power electronic systems. So we'll talk about MOSFETs as power electronic devices in the next lecture.